Hey, good morning, everyone. This is Mr. Aynesworth here at Great Oak High School in Financial Algebra, and we're in Chapter 9, Section 9, the culminating section here, talking about optimal outcomes in a business, okay? And that deals with a subject in mathematics and in business called linear programming. And none of this will make sense unless you did all my prep videos, so we're going to go back here. What you should have done before was this right here, this video series dealing with all the different aspects of linear programming. Okay, it was founded by George Dantzig and a few other guys back in the 40s, and these guys developed a subject mathematics that optimizes a business, and that means to maximize the profit or minimize the cost at the same time. And so this subject in mathematics is very applicable to business, and believe it or not, it has roots in Algebra 1, believe it or not. Okay, I actually teach this to my Algebra 1 students. And so what you should have done was go through all the different aspects of linear programming, where I talk about the feasible region, which is where all the solutions are to your what are called constraints, which is a fancy name for linear inequalities, okay? And so in these examples here, I went over all the basic Algebra 1 principles doing that, just to refresh your memory because it's been a while. And then I also talked about what's called the corner point principle. And like I said before, Dantzig here, okay, the founder of this subject here, or this portion of mathematics that was developed, stated and proved that the solutions to maximize the profit or minimize the cost always lies on the corner points of the feasible region, okay, which is given by these system of linear inequalities. And so that's why I went through here a bunch of examples here with you guys, just going over all the basics of how to graph a linear inequality, define what's called the feasible region, which is this yellow region right here, which is a fancy name for solution region, and then using the corner points to either maximize or minimize something, okay? So you had to go through this first, all right? Otherwise, what I'm about to say does not make any sense. So stop the video right now. If you haven't done so, go in Canvas and go ahead and go through that, because that goes over all the basics, okay? So assuming you've done that, here we go. So number one, and I'm only going to do a selected number of problems here. So part one of my video series is going to be numbers 1 through 4, and I'm not going to do everything. I'm going to do a portion of it. You do the rest, okay? Because you got to practice, right? Because watching me is one thing, doing it on your own is another thing. Remember that. Okay, so notice I have Desmos here on the right. We'll use that when necessary, and we'll use it to verify, okay? Because we can do all of this without Desmos, believe it or not. Okay, we'll just use that as a verifying and checking tool. Okay, so again, Desmos right here, we use it to verify. Okay, what does that mean? It means check, okay? Check results, okay? Sometimes we use it to get results too. So it's used to verify, but it's also used to find results too when you want to speed up the arithmetic. If you're allowed to use technology like this and you know how to use Desmos efficiently, well, then it's a great tool. Okay, so it's used to verify, but it's also used to find results as well. All right, so here we go. Number one, determine whether each of the following points falls within the profit feasible region. Okay, so the first thing you need to know is what this means. Okay, so the feasible region is the region where all the solutions exist. Okay, so it's the region, okay, in which all the solutions exist. Okay, in which all right, the solutions exist. I talked about that in my original video series. So you have to understand the wording here, the lingo, all right? Otherwise, you're not going to know what to do. All right, so suppose that we want to test these points in the profit feasible region given by these three inequalities. And one way to do this is you can simply get a piece of graph paper out and graph these three inequalities. And if these points fall within it, okay, then they're solutions. And we'll do that in Desmos here in a minute. But the first thing I want to do is how do you do it algebraically? Okay, so we're gonna do it algebraically first. Okay, so what you do is you subpoint the point in question into, okay, the inequality and check. That's all you do. Okay, so subpoint into what's they're called inequalities. All right, and check. That's all you do. So let's do it. All right, so what we're going to do is we understand that x is 2 right here and y is 2. They're both coordinates in the point are 2. And what I want to do is check, all right, to see if this satisfies this inequality. Okay, of course, 2 and 2 are both greater than or equal to 0. So both coordinates are greater than or equal to 0. So that I don't have to check. All right, 2 is obviously greater than or equal to 0. It's positive. All right, but does this right here, does this point, when substituted in, does it yield a true statement? All right, so I don't know. We got to substitute in. So I'm going to substitute 2 in for x and 2 in for y and see what happens. So 7 times 2 plus 3 times 2, is that less than or equal to 45? And notice I put a question mark up there. All right, because you're testing. All right, this is an algebraic test. We test algebraically. Okay, you can check it graphically, but you can also test it algebraically. Well, we know that 14 plus 6, all right, is that less than or equal to 45? And the answer is yes, because 20 is less than or equal to 45. All right, and so because of this, this is a true statement. Right here, I'm going to say that this point right here falls within the feasible region. Okay, we're gonna see that here in a minute when we check the graph. We're going to actually graph all three of these. Like I said, you could do it graphically. Right now, we're doing it algebraically. All right, so sometimes they are inside the feasible region, sometimes they are not. And when they're not, you don't end up with a true statement, okay? So for example, in this next one here, all right, x is 4 and y is 8. So here we go. We're going to take this point right here and we're going to substitute it in. Okay, so we have 7 times 4 plus 3 times 8, is that less than or equal to 45? Going to put a question mark above the inequality there. Is that less than or equal to 45? If it is, okay, then we're going to say it lies in the feasible region. If it isn't, we're going to say it's outside the feasible region and it's not a solution, okay? So here we have 28 plus 24. Is that less than or equal to 45? Let me see, 28 and 24 is 52, and 52 is greater than or equal to 45, okay? So this is a false statement. Okay, so that means that 4, 8 is not in the feasible region. So I'm going to say that 4, 8 is not, okay, in the profit feasible region. So you got to make a statement here. It's one thing saying whether it's true or false. It's another thing. Tell me what it means. Okay, so a false statement means that this point, all right, is not in the feasible region, and we're going to see that in the graph. Okay, so how do we do that? Well, we're going to check. We're going to graph and check in Desmos. So graph and check in Desmos. Okay, so here we go. This is what we do, all right? Like I said, it's a checking tool, right? So you need to graph the feasible region first. And of course, in the previous video series, we did this on graph paper. Right now, I'm going to use Desmos just because it's quick and easy, all right? And I'm digital, so I don't have a piece of graph paper for you guys right here. All right, so what we're going to do is we're going to type in this inequality. So type in x greater than or equal to 0. Okay, notice that it's vertical line to the right because all x values that are greater than or equal to 0 lie to the right of the y-axis. Okay, you should know that. Y greater than or equal to 0 means that you're above the x-axis. Okay, so y greater than or equal to 0 is that green region above the x-axis because y coordinates that are positive exist above the x-axis and not below. All right, and then the last one here, we got 7x here plus 3y. And that's going to be less than or equal to 45. So we're going to take a look at this region right here. And it's the darkest region where they all intersect, okay? I'm talking about in this triangular region right here. All right, in the middle here. So what we want to do is see if these points lie within this feasible region. Well, to do that, okay, well, you just set up a table of values. This is cool. So you plot the points. So 2, 2, And notice that's in the feasible region right there. See? It's inside. So we said algebraically it satisfies the inequality. Well, guess what? It's inside the feasible region. And that's why we ended up with a true statement here. 20 was less than or equal to 45 in part A. So 2 comma 2 is inside the feasible region. But 4 comma 8, watch this. 4 comma 8, just type it in. And look at that. It exists outside the region. So 2 comma 2 is inside the feasible region. 4 comma 8 is outside the feasible region. So the algebraic test, if you end up with a true statement, like in part A, 20 was less than or equal to 45, that implies that it's inside the feasible region. So let me go back and state that. So this is a true statement here. All right, and that tells me that 2 comma 2 is inside, okay, inside the feasible region. And the graph shows that, okay? So a false statement, all right, like in part D here, because I tested 4 comma 8, that's outside the feasible region because it does not satisfy the inequality. So you can do it algebraically with using arithmetic, or you can test it graphically using Desmos or a piece of graph paper. Okay? Okay. All right, you do the rest. Like I said, I'm only going to do a few of these here just to give you an idea. You're responsible for B, E, and C. And like I said, there's a lot of work involved here, so I suggest you get your spiral out and do your work in your spiral. Okay? Show all your work and then scan and everything, all your work together, and include it in your submission in Canvas. All right, number 2. The vertices of the feasible region are listed below. Okay, so these are vertices right here. Okay, they're vertices. They're corner points. So vertices, same thing as corner points. So I talk about the corner point principle. Corner points and vertices is the same thing. All right, what is the maximum profit? Okay, so here we go. We have to understand what we're trying to find. So we're trying to maximize the profit in the objective function. Okay, this is called the objective function. So right here. Okay, so the objective, and the reason why they call it an objective function is because your objective is to maximize the profit, and this is called a function. So you input the vertices in, all right, and you see which one maximizes it, all right? You want to maximize, not minimize, but maximize. You always want to maximize profit and you want to minimize costs. So that's why problems 2 and 3 are related, because in problem number 2, you're trying to maximize profit, and then in problem number 3, you're trying to minimize the cost. In every business, you try to do both at the same time, okay? Usually when you minimize the cost, you maximize the profit automatically. All right, but it's a little bit more complicated than that, but in general, that's the way it goes. Okay, so what do we do? Well, we want to set up a little table. Okay, so I would do this in your spiral to show all your work. So just a little suggestion, because there's going to be a lot of work in this section. Okay, so here we go. Let's set up. I'm going to do part A only, and then this on B right here. This is going to be on your own. Like I said, I'm not going to do everything. Okay, so I'm going to set up a little table here, the vertices here. All right, and the objective function here. So P is equal to 120 x plus 170 y. All right, and I'm going to test the vertices one at a time. So 0, 300. So x is 0, y is 300. Okay, you simply take your vertex and you substitute it in where you see the values. Okay, so you substitute in for x, and then you substitute in for y. As you guys know, this is like, all of this is Algebra 1, okay? Like I said, I teach all this subject to my Algebra 1 ninth graders. And if they can do it, you can too, okay? Because you guys are seniors in this class. All right, so here we go. The profit, capital P, is equal to 120 times 0 plus 170 times 300. All right, and then if you just do the arithmetic here, all right, so here we go. So 170 times 300. So the other one's 0, obviously. All right, you get 51,000. Okay, so 51,000 dollarinis. Okay, Here we go. So is that the maximum profit? I don't know. Okay, so you have to test them all. So here we go. So 0, 0. Well, that's not going to give us anything. So 120 times 0 plus 170 times 0. Well, that's just 0. So that is definitely not the max. 0, 0 will never be the max. I mean, that means you don't sell anything, you don't produce anything, you're not going to make anything. And then the other one here, 1200, 0. So what's the profit there? So it's 120 times 1200 plus 170 times 0. Okay, so here the profit's going to be just 120 times 1200. That's simple. It should be 144 with 30, 144,000 maybe? I don't know, let's find out. Okay, so 120 times 1200, 144,000. Okay, so now 144,000 is bigger than, all right, bigger than 51,000. So this right here is called the max profit. All right, and so it occurs at, all right, at the vertex right here. So this profit occurs at this vertex. So we say at 1200, 0, where x is 1200 and y is 0. And that's important to know because these numbers are going to mean something here in a real problem. And you have to know what 1200 stands for and what y stands for. And in a real problem, in a real context, these numbers have to be interpreted. So it's one thing developing the numbers, like you compare 51,000 to 104,000. Obviously, 144,000 is bigger. All right, so that gives you the maximum profit in this case. All right, you do B on your own. Now let's take a look at C. C, or 3, is very similar, but this is a cost function. And you want to minimize cost when you run a business, okay? So we have a cost function right here. This is the objective function again. But we're going to minimize the cost. C for cost, P for profit, okay? So we call this the objective function, and our objective is to minimize the cost. That's why they call it an objective function. So you're going to take these vertices here, these are vertices, all right? You're going to substitute it into the cost function, and you're going to minimize it. So again, so we have vertices here, and I'll do A and you do B. Okay, you got to do something on your own. And we're going to write our cost function right here. So I'm going to write down cost. Cost is equal to 57 times whatever x is plus 88 times whatever y is. All right, so here we go. So 2, 9. So my cost is going to be equal to 57 times 2, all right, plus 88 times 9. Okay. Now I'm going to pause here. You can do this in Desmos the long way. All right. Okay. So one way to do this is to simply type in 57 times 2. All right. And then add 88 times 9. Okay. You could do it this way. And you get 906. Okay. $906. So $906. That's your cost. Now the question is this the minimum. We want to minimize, right? So there's another way to do this. I want to show you, and I did do this in number 2, but I want to show you how to do this for number 3, and you can do it again for number 2 when you're ready. All right, so what you do is you set up a table. So I'm going to click on the plus sign here. I'm going to click on table, and I'm going to enter in the 4 points. So 2, 9, and then the next point right here, it's going to be 10, 20. Just read the problem. And the next one, 15, 13. And the next one, 8, 2. So you type your points in, and then you write a function for the cost. Now the function, the objective function, is 57x plus 88y. But notice our values are in x2, y2. All right, so you could type in 57 here times x2. So you type in exactly what you see. All right, plus, and then 88 times y2. And what happens is it evaluates the function for you. Isn't that nice? Okay, so being a little sarcastic right there. But notice, look at that. So you have all the results here for you. Right here, you can write these down, obviously, in your spiral, but here we go. You can do it by hand, and you can also use Desmos very effectively. Okay, so this is using Desmos and the table mode. All right, check that out. Now you're trying to find the minimal cost, or the minimum cost, and if you understand that this is a cost function here, this is your cost, so you got to compare these. These are in dollars, of course. So what is the minimum? Well, it kind of looks like 632. So this right here equals the minimum cost in dollars. Okay, so minimum cost in this one would be $632. Okay, and you could do part B on your own. So you can step it out like you normally do using just basic operations, or you can use table mode in Desmos. Pretty effective. And you could do the same thing in number 2. You can put the profit function in and evaluate a bunch of points to figure out your maximum profit. Do it really quickly here. Okay, dun, dun, dun. So showed you how to do it a couple different ways there. All right, let's move on to number 4. So in each of the following here, you're given an objective function and the vertices of the feasible region. Okay, cool. So right away, I can just see that we have an objective function here. This is going to be profit right here. P for profit, C for cost. And this is called the objective function because your objective is to maximize profit, or it's to minimize cost. Okay, so you want to maximize this and you want to minimize this. Just keep that in mind. Okay, it says determine both the maximum and the minimum values of the objective function as well as the point at which they occur. Okay, so let's do that. Okay, so let's go into Desmos here. All right, so I'm going to do it the technology way here. Okay, so I'm going to click on here. I'm going to go into table mode and I'm going to put my vertices in. Okay, so these are my vertices right here. Okay, corner points of the feasible region. Okay, it says vertices of the feasible region. That's this right here. And that means they are solutions to the inequalities. They are solutions to all of the inequalities. All of the inequalities. Okay, now we're not given the inequalities here, but this is right here is just testing your knowledge of what to do with the vertices. Okay, you substitute them into your profit function and maximize it. Then you substitute the other vertices into your cost function and minimize it. That's what you do. Okay, so let's put in the points in here first. So 6, 3. I'm obviously working on part A here. Okay, and then next one is 10, 10. I'm using my digital keyboard here. And my next one is 15, 7. So after that, you type in your function. Now my function, my profit function, is 81x plus 57y. But notice my data is in x3, y3. So I have to adjust. So 81 times x3. All right, because my x values are in the column, the first column there, which is labeled x3. And then plus 57y, so 57 times y3. And voila, it gives me my values. So nice, so nice. Okay, so let me grab this here and bring it in. Gotta love technology. Okay, when it works. Okay, because sometimes it gets a little crazy. So let me bring that in and annotate it right here. Okay, so this is obviously for part A. So this is my profit function here in part A. And so the minimum right here is 657. Okay, that's my minimum. This is my minimum profit. It says find both minimum and maximum. So we know the minimum profit is $657. The max profit, all right, is $1,641. It says determine both the minimum and the maximum. Okay, so you have to read the directions here. Okay, so I found the minimum profit, I found the maximum profit. It's that simple. So you type your vertices in. These are called vertices, which is a fancy name for corner points. All right, and you minimize or maximize the profit. You do the same thing for the cost too, but in this one here, obviously you have a different function. All right, so when you run this one here, again, you just go into table mode, you pick a table, put your data in, and our data set's a little bit bigger, so we have 0, 800. We have 40, 1,000. We have 100, 900. We have 60, 200. And then we have 50, 50. So you type your data in, and then you write your function. Now this time we have a cost function, and the cost function is 98.15x. So 98.15 times x4 now, because our data is in the fourth table. Okay, this is our fourth table, plus 63.5 times y4. So 63.5 times y4. So you just type it in, all right? Use the correct subscripts for the correct data table, and it gives you the values. All right, so let's bring that in and let's annotate. All right, so here we go. Let me grab my data table here. Okay, so here we go. So let's see what we got here. So this is my cost. These are my vertices here, my verts. All right, and we want to find the minimum and the maximum. So if you compare all of these right here, let's see here. Our minimum right here is $8,082.50. So this is my minimum value. Of course, it's the minimum cost, because that's smaller than all these other ones. I mean, compared to 18,589, 66,965, 67,000, and then 50,800. I mean, 8,082 is a lot smaller than all of those. And then the biggest one looks like here we have, oh, not 66,000, we have 67,000. So this is my maximum cost. Right, 67,426 is bigger than 66,965. All right, so again, the directions say determine both the minimum and maximum values of the objective function. All right, and that's exactly what I did. I found the minimum and I found the maximum on the cost. And then over here on the right on part A, I found the minimum profit and then the maximum profit. There we go. And you could do it by hand, or you can use Desmos. Here, I used, all right, the Desmos, as you guys just saw. So learn how to use the technology properly, and it could be to your advantage. Okay, that is part one. I'll get into the big part here in my next lesson here, coming up next. Okay, so get ready for that. This is Mr. Aynesworth again at Great Oak High School. I'll talk to you later. See you soon. Take care.